Dear world, welcome back to the next session of the data structures and algorithm basics. So previously we have understood the abstract data types and we are supposed to discuss the asymptotic notation in the next session. So this is exact that session where we'll be covering the asymptotic notations, the representations and the three types of siblings of the asymptotic notations, the big O notation, the big omega notation and the exact theta notation. So without further wasting time, let's look at the board. So in today's session we'll be understanding the big O notation. So we have already called the big O notation the seal notation, big O omega notation the floor notation, and the theta notation the exact fit notation. So I think you have clearly got an idea from the name of these notations or the ideology. This is the word and that's the function of them. That is big O notation the seal. Seal means what? The top upper bound. Where suppose this is a room. Let's say this is a room. This is our room. So if you call it what is the seal, so seal will be our roof, so this will be the seal. Seal, that means what? So this is the ceiling of our room. Ceiling, that means the upper bound of our room, so that we call it the upper bound of our room. So now we got the upper bound of our room, and in programming language this upper bound we represent by utilizing the big O. We represent this upper bound by using the notation big O. So this, now let's say we'll be defining simply by big O notation. So now we have got the upper bound. Now we'll be talking about the lower bound, the floor. So if we call it this is our floor, and so we call it the floor in our room language. So but if we call the same floor the floor level of values in programming language, so for to represent that things we use big omega. So this is our floor. Floor, that means what? Lower bound of our room. And to represent this lower bound we use the big omega notation. So that is big omega. And now let's say something exact fit. When if we do, now we are taking in our ambition, we are in dream. Now we are, let's say we are dreaming. We are dreaming. And in our dream what happened is that the upper bound and the lower bound became one. That means our room came into the just one line. They become like this, and the upper bound and lower bound they got collapsed. That means they got exact fit. So we will be representing the things by utilizing the theta notation, because that is the case in our dream of exact fit. So this case is exact fit, and this exact fit will be represented by the theta notation. So you have got a very basic idea about the exact fit notations. Now we will be going deep into all the asymptotic notations. So I've already told about big O notation, the seal notation. This is the seal notation, big O omega notation, the floor notation, and theta notation, the exact fit notation. Now let's try to understand those notations in terms of our programming language. Now I will give you another second example. Before we go into the graphs and look complicated things, let's try to understand in second example. Example number 2. So let's say I will be considering we are students and we travel by lift. So let's say in our college we have a lift. So this is our lift, and the maximum capacity of the lift, this is lift, and the maximum capacity of this lift is maximum capacity, that is 10. So in there might be various cases when student people can go to the lift. So this is the capacity that we can go. Highest it can take only 10 employee. So sometime it can be that in some day or sometime the lift carrying exact 10 people. It is carrying the 10 people. Sometime it can carry 10 people. Sometime it can also happen that the lift is carrying only 1 people. The lift is carrying only 1 people, not 10, just 1 people. So now notice, sometimes this lift is carrying 10 people and sometimes it's carrying 1 people. Okay, So there is two cases, that it is carrying 10 people sometime and second time it is carrying only one. So we can represent these things as a function. That is what lift is going up and it's coming down. That means it is a function that is being operated. So we can represent this function by two types of notation. Lift carrying 10 out of 10, that means this is the upper bound case. So we can represent this capacity by this big O notation, that is big O of lift carrying, big O of lift carrying, that is equals to 10. That means what, we represented the upper bound value, and when the lift is carrying 1, then we will be representing big O of big theta of lift, I mean big omega, sorry, big omega is the floor, so we'll be representing by omega. So this is a flooring lift carrying. So flooring is what, the lowest value, so it will be 1. So we are representing the same function by utilizing two types of things. That is, now let's say another case. Here we just observe two cases. Now we are taking another lift. This is lift, and this lift has a capacity of carrying 5 people. This lift can carry 5 people. Okay, this lift can carry 5 people, and if we want the theta value, that means exact value of lift carrying, then what we will get, it can carry only 5 people, so it will always provide at the answer the 5, that means the exact case. So this is the things that will be looking. These notations are nothing but these are the three representations by which we represent the best case, the worst case, and the average case. We represent the worst case by utilizing this big O. When we represent the worst case. We represent the best case by utilizing this sigma notation, and the exact fit case, we represent the exact fit case by utilizing theta notation. So now we will be looking in more details the big O notation. So let's study what this big O notation tells. Big O tells you the maximum speed. Big O tells you the maximum speed at which your algorithm time or space can grow. It's the worst case scenario. So in programmatical language, Big O tells us that the maximum speed at which our algorithm time or space can grow. So in programming, whenever we solve any algorithm, we only deal with two things: the space complexity and the time complexity. The space complexity and the time complexity. So these are the only main two factors what we deal with in our programming language, and every time our motto is to reduce those, and to make very high performing codes, to have high performing algorithms. So that is, so Big O tells what, the maximum speed at which your algorithm time or space can grow. That means if, let's say this is our algorithm, 3n square plus 5n plus 2. So there are a lot of factors, but what can be the highest time taking? It can only be n square. N square is the highest time. So our big O notation, it will only represent big O of n square. That means our this algorithm can take the highest time of n square. So it is represented by utilizing big O notation. Now let's move to the ceiling notation. So this is the same example, the ceiling big O notation. Imagine you are in elevator, maximum load 10 people. If there are 3 people at host, it can hold 10. So this is the same example that I gave, that it will, if there is 10, I mean if the lift is carrying, there is lift 10, the lift has a capacity of 10 and it is carrying 3 people. It is carrying 3 people. So if you ask that what is the big O value of this lift carrying, so big O value will always give the maximum value. It will still provide us 10. So that is. But if we ask what will be the sigma value, if we ask, so it will always provide at the least. What can least provide? That can either be 0 or 1. And if we just ask the sigma value of this lift carrying, so sigma value is what is the least value, that means what is the least number of people required for this lift to go. It must be 1. When there will be at least one person in the lift, only then the lift can go up. So sigma value will be getting the 1 and the exact value. And if you ask the, this is big O, and if we ask the big theta value, that means the exact value of this lift carrying, so we'll get the exact value of 3. We'll get the exact value of 3. So this is what's told here. Now we'll be looking at the floor big omega notation. The floor big omega notation. Big omega tells you the minimum speed your algorithm will grow. It's the best case scenario. So big omega tells us the minimum speed. It tells the minimum factor our algorithm can grow. So if we care about the minimum factor, if we care about the minimum factor, this big omega always represents us the minimum factor by this big omega notation. This is used for best case complexity. We utilize this big omega for representing the best case complexity. If an algorithm takes at least n steps, suppose an algorithm is taking at least n steps, if an algorithm is taking n step, then we will be writing sigma of n. Now this is the same notation. Imagine you are in an elevator maximum load 10 people. So the example, if this is having capacity 10 and there is only 3 people, so there is 3 people and we ask the omega factor, the least factor to it, this one, omega of carrying capacity. So this gives us the best case that when that will be only 1, then it can run. So it will provide us a value of 1. You must have one person to move. And now we'll be observing the exact fit theta notation. So theta is when your algorithm's growth rate is both bounded above and below by the same order. So as I've already told you that when our growth rate, let's say this is our algorithm, this is a function, let's represent by this. So that is a function, this is growth rate, and this is this. So this is the best case, big O of this function fn, and this is the best case. Let's call it the time requirement. So it is taking the lowest time, it is taking the base time, but in this range both the value has been collided. So in this intermediate region we can call it the big theta, or the exact position of this function. That means this is just a typical idea that what is the exact. This is not the the example is not fitting that way, but this is the idea to give you. Theta is when your algorithm growth rate is both bounded above and below by the same order. That is a tight bound. Theta always represents a tight bound. So that is the theta. If we just get theta, that means that is the tight. That means. So meaning both upper and lower bound used for average case complexity. We utilize this theta notation for exact growth rate or exact case.